All right, welcome back. Thanks for showing up again. This room definitely looks too small. But I guess that's a good problem to have. So hopefully the camera angle is a bit better now that it's not looking up directly at me. This isn't terribly ideal, but I guess it's an improvement. When we last left off, you were all at the edge of your seat about that little executable, so we'll figure out why that works today. Just a bit of also housekeeping in the Discord. So on Quarkus, there's a link to the Discord too if you haven't joined it already. If we can set office hours, that would be great. It looks like so far Tuesday is the leading day for this section. So if you want to throw in your voice for that, because section 2 has outvoted you thus far. So if you don't want it Tuesday, please go in the Discord, vote, and then if it still looks like Tuesday, I'll put on some time suggestions and we'll figure out what time to set them. So yeah, and also throughout the course, just another bit of housekeeping. I'll hopefully make the lectures fairly interactive and post code that you can try yourself, mess with. We'll screw it up during the lectures. So I'll just post it all on GitHub. It should work. If you're using Linux or Mac OS, if you're on Windows, well, I hope you have a virtual machine. So they'll be posted there again, right? This is in the slides. It's a link. You can click it and all that good stuff. So to kind of elaborate on what exactly an operating system is, because that operating system had kind of that fuzzy boundary where it kind of depended on what application it was. Well, the part that is very not fuzzy is what a kernel is, which I didn't really explain yesterday, so here's the explanation. A kernel is the software that runs in kernel mode. So on your CPU, there's different privilege modes on your CPU that controls what instructions you can access. So thus far, you've been writing programs in user mode, right? You write a program in C, you compile it, you execute it. It runs in what's called user mode. So that's like kind of the general CPU operations, you're allowed to touch them. If you happen to write your own assembly by hand in your program, which I don't know why you would do that, I think I'm the only one crazy enough to do that, you couldn't access some instructions that tried to interact directly with hardware. If you tried that, you'd get an exception, the operating system would yell at you and you wouldn't be allowed to do it. But the code that can actually execute those instructions have to be running in something called kernel mode. So those are all the instructions that interact directly with the hardware, and it's separated so that you are not allowed to touch them and only the operating system can touch them. So the kernel is a part of the operating system that runs in kernel mode. It is the only software that is allowed to interact directly with the hardware because it's still running in user mode, but it's like a privileged user that can do more stuff. So we'll see a bit more later when we get into kind of the whole rest of the file system, but pseudo stuff still runs in user mode. Yep.
Wouldn't it make more sense to have the rings inverted? Because everybody should be on the outside because it encompasses the inside?
Yes. Yeah, I mean, you could write them any other way.
Oh, okay, so just, okay.
Yeah, I guess it might make more sense. I don't know why the convention is to do it this way. But basically, so you're in user mode. You can access your instructions like add, multiply, so on and so forth. And then in kernel mode, you can access instructions that deal directly with the hardware. And also in that mode, you can access all the instructions in user mode. So if you write kernel code, God forbid, you can still use all your normal C things, which is why the kernel is written in C. And this hypervisor thing, you might notice is kind of weird, and we'll get into that way later in the course. So the kernel of the operating system runs in kernel mode. It is a very important part of the operating system because that's what can talk to hardware. So there's this clear kind of separation between user space and kernel space. So far, we've only been dealing with user space. No one has called into kernel code, at least directly, that they know about, even though you have. So the way to kind of bridge this boundary is with something called a system call. And that is the only way to transition from user mode to kernel mode. And all your applications had to have used this because they interact with something. They show you something on the screen. You get output from your hardware. So eventually, whatever you do in your program goes to kernel mode, and you have not been aware of it thus far. So that's kind of where this course is going to live, kind of at this boundary between user space and kernel space, and kind of explaining what the interface is between them. You'll be writing programs that are in user space that kind of more directly use system calls, and you'll kind of understand in this course what is going on in kernel space without having to write any kernel code because, whew, it gets kind of bad. So for right now, you can think of system calls, right? They just behave like regular functions. They're C functions, but everyone loves C, right? So they're pretty much C functions. So we're going to look at two today. So we're going to look at write, which is one of the system calls to communicate. So if we look at the signature, it takes 3 arguments. The first one is a file descriptor, which is just a magic number that represents something that we could write bytes to or read bytes from. In this case, since the system call is called write, we are putting bytes somewhere. So whatever number is associated with the file descriptor, that's where we're going to put bytes. And it's just an integer, so believe me, just a number. Second argument is, a pointer. So this is why we all have to get used to pointers. So it's just a pointer to some data. Void star is just C's way of saying it's a pointer. I don't care what the data is. It's just a pointer to something. So the second argument is just a memory address. And then the third argument is how many bytes to take from that address to write to that file descriptor. And error, it's negative, and you don't have to know that for now. The second one is called exit group that takes a status, which looks kind of familiar to how you have written C programs. Kind of looks like main, although how did you exit from a C program?
Exit 0.
Return 0. Yeah, so you just return from a main, but if what I told you is true and you have to interact with kernel mode and this is how you exit out of your program, you know that when you return from main, eventually whatever number you return there makes it to this exit group and just copies the number and then does that call for you. So already that's one of the things C does for you. It saves you from having to write these system calls, and like we saw in the kind of first lecture, the solution to every problem is just a layer of indirection. So if I have to write a programming language that runs on multiple kernels, well, I don't want to write system calls. I will just make up something called the C standard library, which would be a layer of indirection. And then instead of calling system calls, you could call into the C library. So that's another reason why it exists, that layer of indirection. And then exit code just has void. In actuality, your program's dead after you call exit group, so it doesn't actually return from this function. Your program's now dead. So let's go ahead and let's just execute our program again just to make sure. I rearranged it a little bit, so let's make sure we're all on the same page. So everyone can see that right at the back? Nods, okay. So if we execute our hello world, we're on Arch, right? 58 bytes, so we should be able to understand it. So a file, right? A file is just a format. It's just a bunch of magic, kind of. So a file is just a bunch of bytes, and the only way the operating system knows what a file is essentially by reading the first 4 bytes. And if there are some magic bytes there, it knows what that file is, and then assumes the rest of the bytes in the file follows some specified format. So on Linux and like FreeBSD or PlayStation, whatever, has an executable format called ELF. If you're Mac OS, it uses something called Mach-O. But for this course, we'll just stay on Linux and assume everything is ELF. So if you read, it is like an ASCII escape code, so it doesn't try and interpret the rest of the file as text. And then it's followed by the ASCII letters ELF, and that's the only thing that specifies it's an executable file. It's kind of appropriately called magic. And this is how like every single file on your computer works. You'll notice that if you change the extension, at least on Linux, it doesn't change what you can do with the file. You can call it JPEG whatever, and you can still open it. JPEG will follow the same thing like this. I even think it starts with the same byte, and then it's just like JPG. And if it starts with that, hey, it's a JPEG. I should interpret the rest of the bytes as kind of pixels. So there's some other stuff in this header file. We don't have to overly concern ourselves with it. But basically, any file is just, a bunch of magic. So if you want to kind of read into the executable file format a bit, I don't suggest you really do it. This is kind of just for curiosity's sake. You can use a command called readelf that will give you all the information about it. It contains, a header file which has things like what operating system should this run on, what architecture did I make this for. Most importantly, it has the entry point of the program. So what instruction should I start executing at, which will basically initialize your program counter, right? It has some other stuff in it. It has like program headers that are required for executables and section headers that are required for libraries. You don't actually have to know. The long and short of it is there's a header file, and if we try and explain every byte in that 168-byte program, the header file is 64 bytes, and a program header is 56 bytes. So there's kind of 120 bytes, which is most of the file. It's just some housekeeping information. The header file just says, it's an executable and where to load it into memory, and you get to specify where you want to load into memory. You have complete control. You have complete control over it. If you use C, right, it just picks something for you. But in this case, if we just write an ELF file, we have control over it. So if you read the program header, it basically just says load the entire file, that the 168 bytes, into memory, starting at address, was that like 10,000? Yeah.
From like last lecture, you said there was like this virtualization. So when we tell it to read it at this address,
yes.
Does it actually need that hardware address?
No, so this is all virtual addresses. Yeah, so good point. So these are all virtual addresses, and you see, if I was fast, you could run multiple of these at the same time. They're all going to execute at some address, right? But they're all going to be in different places. And if you write, like your web browser is an ELF file, you can read that. It has an entry point address, but you can open up many Firefoxes. And through the magic of virtual memory, which you'll see way later in the course, it just magically works. So 120 bytes are just header information that basically says what it is, and we're going to load it at address 10,000. So the next 36 bytes are the actual instructions, which is kind of what you wrote in your computer organization class, right? You did a little bit of assembly, right? Yes, I see some nods. So that's your whole assembly. So you should be able to understand that assembly, right? No problem. So there's some instructions there, which are 36 bytes, and then the last 12 bytes are for hello world, and that's just the string. So hello world, right, has a new line character at the end. So if we load everything at address 1000, instructions would start at 120 bytes in, because it's after all that header information if we just put them in the same order. So the instruction should start at 10,000 hex 78, and then the string should start at 10,000 hex 9C, right, which is 156, because it's after all the header files and after the instructions. So does this make sense, hopefully? Good question. So in this case, I just picked arbitrarily. So if I wanted to, since I wrote the bytes in this because I'm sadistic, I could have put the string at the front. And if I put the string at the front, all I have to do is change these addresses, right? So I have to make sure the entry point is after the string, and then I've referenced the string, right? and 0 is reserved. So 0 is your null pointer. So the operating system, you'll see kind of how it organizes virtual memory. Essentially doesn't let you touch the first page, which is 4 kilobytes. So you have to at least be over 4 kilobytes. And sometimes it depends on the architecture too. Yeah.
So even if we're doing it in assembly, all of the memory would be, like all the addresses are virtual memory as well?
Yeah, because we're just running on Linux. So all the user programs, everything uses virtual memory. The only way we would use physical memory is if we were writing the operating system ourselves. Or you had an embedded machine that doesn't even have a kernel or anything, right? You're just programming directly to memory. Okay. Oh, yep.
Sorry. So it's the first 64 bytes that tell it what file is, or the first four bytes? I'm kind of confused. What was the first 4 bytes telling you that the first 64 isn't?
Oh, so the first 4 bytes just says it's an ELF file format, and then this first 64 bytes, including that magic, is the header file for the ELF format.
Oh, okay.
So it's part of it, and within the rest of the header, it'll say like what the architecture is. We can see here, let's pull it up real quick. So if we do a read ELF on that executable, -A, oops. So essentially, everything up here is all the information that is in the header file. So it says, hey, it's in 2 complement little endian, right? It's version 1, which it's been version 1 since like whenever this was invented. So the operating system is Unix. It's an executable file. It runs on AArch64. And there's our entry point. So it's contained within the header. So we can see we're starting at the first instruction we define. And then it also defines like the size of this header and size of program header, which is kind of weird because it's defined in the file, in the format itself. So they kind of over-engineered this a little bit, but you know, it's only 64 bytes, so I mean, who really cares? And then this is the program header, which you don't have to read it. Basically, it just says, load everything into address 1000. You can use this readelf though on, you know, the executables that C produces, and you can see all the other magical stuff C inserts into it. Yep.
So kind of like the smallest possible program is like 65 byte, because you need 64.
Yeah, so yeah, there's hacking you can do. So you need 64, and then you need the 56 because it has to tell it where to load into memory.
Oh, so you need 56.
Yeah. There's like a blog post somewhere of people really hacking this format because Linux kernel doesn't like strictly follow it. And there's a lot of zeros in the header. So you can actually shove all the instructions in the zeros and then reuse it. But it's super sketchy. This is like the smallest thing that actually is compliant. But we'll explore kind of what C does. But kind of as I said, we're going to be living at that system call interface, so I'm going to teach you the command that will get you through this course and even help you whenever you're programming literally anything, because any program you write is going to have to go through this interface. So if you want to kind of see what system calls your program's using, and you can have fun, you can do this on all your different programs, use a command called strace, and it shows you that your program makes. So if we do strace on our little executable, spoiler, we'll see this next lecture, don't worry about it. So our program makes a write system call to magic file descriptor 1, y1, because, and then the second argument is, if it's a string, it'll try and print it out nicer for you, but remember that's just a pointer. So it shows that we're printing hello world with a new line, and then 12 bytes. And then after that, we do exit group with 0. Also, can anyone tell me what's weird about this string as opposed to how you've been using it in C? Is there any notable difference here? So what do strings always end with in C? Yeah, null, right? A 0. C just decided that. You don't have to do that, right? That doesn't have a null at the end of it. If you look at this, right, it goes all the way to the A, which is a new line. So null terminated strings are just a C convention, right? You don't actually need them. Okay, so quick aside, so we'll be using that strace a lot, especially if you need to debug something. But just a quick aside, the difference between an API and an ABI. So an API is more abstract. It just kind of tells you what something is. So for example, what I showed at the beginning was an API, right? I just showed like a write system call and its arguments. I didn't give you any details if you actually had to implement it, right? Because everyone did function calls in that computer organization course, right? And you laid out your arguments somehow in registers. So how you lay out in registers is actually called an ABI, and if you need to make system calls or do C calls, there's a specific ABI that tells you where to put all your variables and everything like that. So yeah, the ABI is just how to lay out the data, what arguments go where, so on and so forth. So you set up some registers, made your call, and then there were caller saved ones, callee saved ones, which is kind of a pain, but we don't have to know those details. You've survived all those details, so you get to ignore them now. So, and the C calling convention, right, instead of using registers, it uses a stack, but probably won't be relevant for this course. So the system call ABI for Linux, just so you can, if you ever wanted to write this in assembly, which again, you don't have to, I'm just slightly sadistic. So you enter the kernel with an SVC instruction, and basically this is the only interrupt you are allowed to raise in user mode. So SVC is a supervisor request, so it's like you need to call your parents or something like that. So if you execute an SVC instruction, the interrupt gets raised to the kernel, right, which is new, so it gets to handle the interrupt, and then it could go through and actually perform the system call. So before you call this SVC instruction, the calling convention is it passes arguments through registers. So the X8 register is how you specify what system call you want. So each system call just has a number associated with it. And then registers X0 through X5 are just argument 1 to 6. So anyone tell me what an obvious limitation of this kind of ABI is? Yeah.
Only pass 6 arguments to any function.
Yeah, so if I have 7 arguments, right, I'm screwed. So if you wanted to do 7 arguments, right, you'd have to do the computer science solution and go through a layer of indirection. So you could just pass a pointer through one of those that had like a more elaborate data structure if you wanted to pass more data. But for this, you only have 6 arguments you can use. And they're also all one size, right? They're all 64 bits, and you can't change it. So if you had a smaller data type, too bad, you're going to waste, the other bits. Oh, yeah.
Sorry, just out of curiosity, 2 slides ago you were talking about like the C calling convention, which just kind of goes in the stack.
Yeah.
But I kind of read that like compilers optimize stuff that it goes in registers and stuff. So is it like?
Yeah. So there's, okay. This is like compiler course. I'll answer it anyways. So there's like a C calling convention that uses a stack, but there's also other C conventions that have fast calls that will use registers. And your compiler's smart enough to use those if they're available.
Oh, okay.
Yeah, or sometimes they'll just get rid of a function. But yeah, but the standard, no optimizations, no anything, it'll use a stack. All right, so if we plug in the actual instruction bytes into a like online disassembler, it looks something like this. So all we're doing is moving values into registers. So X8 was the system call number. So if you look it up in the table for this, system call 64 in decimal, which is 40 in hex, is the right system call, right? We wrote it to file descriptor 1, so we would put the value 1 into X0, and then next we move kind of the lower bytes. Because this is ARM, we have to do a move in 2 steps. So the first move instruction will zero out all the other bits and put in like 0000009C, and then move K will not touch any bits except for what it's setting. So between these two instructions, it will set x1 to 10,009C, which is the location of our string that we saw before. And then there's a typo here that I have to fix. We move the value 12, not 2C, into the third argument, which is how many bytes to actually take from that memory address. And then we call home, we do an SVC, and then this would do the write system call. So we're in user mode. This would prompt an interrupt to the kernel. The kernel would go ahead and handle it. It would look at all the registers, see that we're doing a write system call, execute that write system call all in kernel mode, and then when it's done, it would put the result back in some register and then return to us. In this case, when we use strace, it returned 12 bytes that it wrote. In this case, I just kind of ignore the return value. I just assume it wrote the bytes. I don't do any error checking. I assume none of you, has anyone ever error checked printf? Okay, so I'm not alone. I didn't error check anything. So printf can fail. The kernel can just refuse to write bytes if you want. And then, so that's our write system call up to this SVC. And then we do the exit group. So if we look up, 94 is the number for exit group. You might be asking, why is it called exit group instead of exit? And the answer to that is we'll figure that out once you know what a thread is. And then, right, it only takes one argument, so we put 0 into x0 and then do an SVC, which would exit and then kill our program. Yep.
So when you use the SVC instruction, that's how does the kernel or whatever know that that's the correct instruction, like that you're supposed to be able to access the kernel mode?
So that's the only interrupt you're allowed to raise in user mode.
Okay.
And then the kernel has special interrupt handlers for that code.
Okay.
So as soon as you raise it, the kernel will figure out, it will intercept it and then handle it. In this case, it would do a system call. There's other things you can do that trigger the kernel, like do a null pointer exception or something like that, in which case, you'll seg fault, and then the kernel will handle that and kill your program.
So I have a question. So whenever you call SSC, it basically takes whatever instruction stored in X8 and goes ahead with that.
Yep. Yeah. So if you want to, explore random system calls, you could put random values in there if you want. Weird stuff's going to happen if you don't know what you're calling. And there's only 451 of those, so there's only a few you can do. But yeah.
Sorry, what is the 0 for the SVC 0? Does that matter when you put in 0 there?
Oh yeah, so that's a good question. So that's for more general purpose stuff. For this, the value doesn't matter. So you could put, it just does a placeholder value, and 0 is as good as any other value. Okay. So if we finish up our example, we only have 12 bytes left, and that's, of course, the string that's ASCII encoded. If you have to look at ASCII strings a lot, which I feel sorry for you if you do, but if you do, a quick little hack is you can always see if something's a lowercase or uppercase by looking at byte face was a pain unless it was just one bit. So very efficient back in the day. So that's every single byte of our program. So let's go ahead and see what C does. And I preempted this, so we already saw that, in this, null terminated strings aren't a thing the kernel doesn't care about. So let's go ahead and see what C does. Okay, clean. All right, so I just have the plain hello world, right? If I execute it, it looks like hello world. If I want to see what's really going on, what command should I throw in front of it? strace. On, let's throw an strace. So let's see the overhead of C. So if we run strace on what C compiled, it kind of barfs. It throws a lot of stuff up at us. But at the very end, we can see here that it does exactly what we did before. It writes 1 to hello world, 12 bytes, gets 12 bytes back. Who knows if it error checks? We just called printf. And then does exit group. And then it does a lot of stuff beforehand. So let's see kind of what C's doing. So here's all the stuff it did. So we're starting here. So if we start up there, let's see if we can just kind of guess what it's doing. So BRK, we don't know what that is. mmap, we have no idea. Caching's good. That's all good. It closes it. Then this looks somewhat familiar, right? Anyone guess what that is? Yeah.
That's the standard library, right? It's loading in the standard library.
Yeah, so that's your C standard library. So it opens the C standard library and open returns a file descriptor. So it just gives you the number 3. And then you can see that it reads 3. And then you can see that it's an ELF file, right? So these 4 things here, it doesn't look like 7F because this is written in octal for some bizarre reason. But that's 7F. Don't ask me why they want to display things in octal. It was cool back in the day. And luckily, that's before my day, too. But you can see this is the escape code and then ELF. So it's an ELF file. And then it just has a bunch of information. So the C standard library is an ELF file like everything else. And that you can see. So it read something from the standard library. It does some kind of magic here with nmap. Spoiler for later in the course, mmap is kind of how you manage virtual memory. But for now, we don't care about it. There's some nmaps. We're protecting something, closed. Set some address, who cares? We don't know what any of this does. Yeah, C makes things much simpler. Now if we get to the end of this, it gets a random number for some reason. And then here, so everyone knows what a heap is, right? So like there's a stack and a heap in our standard program. So you've never had to manage your heap before, right? Yeah, everyone's used malloc, and that manages the heap for you, so you can allocate stuff. So, right, if you just write an executable yourself, and you don't have the niceties of the C standard library, you have to manage your heap. So BRK actually gives you the address of your heap. So if you call it with null, it returns where your heap starts. And then this is how you allocate and deallocate. You just grow your heap down or up, and that's it. So this is malloc essentially allocating space for a heap for you. And thank God you don't have to manage it, because that would be awful. If you thought malloc and free was bad, try managing the heap yourself. It's truly awful. But then after all that, it goes ahead and does what we expect it to do. And you can do this with literally any other thing. If you write hello world in any language, you can use strace on it and see what it does. I guarantee you that if you write strace on something in Python, it will be even larger than that, and it will also load the C standard library. If you run strace on some JavaScript application, it might be a few gigabytes, because yikes. So we did that. So basically it finds the standard library, loads the standard library, then it sets up the heap and then prints the values for us, right? But at the end of the day, the only 2 system calls that actually matter are the write and the exit group. So you can think of the kernel as just a long running process too. It's the only difference between a kernel and what you write is just it runs in kernel mode. But if you want to add code to the kernel, it's a bit weird because it starts before anything you can do starts, right? So if you want to add code to the kernel while it's running, you can't use main. You have to kind of, in kernel parlance, you have to create a module, which is essentially kind of a library, and then you tell it what code executes when you load it. When you unload it, you can have the kernel call that code when new hardware is added, and so on and so forth, just to make it a bit more modular. Otherwise, you can tell if something is running in kernel mode is if you update it and then you have to restart your computer, then it was probably some kernel code. Because otherwise, you can't just restart it, right? It's one long-running process that survives as long as your computer is on, right? But if you go ahead and write a kernel module and insert it in the kernel, you are running in kernel mode and you are allowed to do anything you want. So you have to be careful, and that's why debugging it is kind of a mess. Because if you have a null pointer exception or something like that, and it's all running in kernel mode, your kernel dies, your computer dies, good luck debugging it. And you could also do weird things. You could just kill everyone's program running on the machine if you wanted to, if you touch a special file, right? There's lots of weird things you can do. So there's different ways of organizing the kernel. Like the only thing for sure is the kernel runs in kernel mode, but there's kind of a debate about how much code should actually run in kernel mode. The easiest thing to do is say anything that has to even remotely deal with hardware should run in kernel mode, and that's called a monolithic kernel, and this is what Linux does. So it just puts everything in kernel space, so if there's a bug in anything, it just crashes your kernel, but luckily they're very good at writing, hardware code. So it'll do things like manage what process is running, so what program's executing at any given time. IPC, which is just how processes communicate together. File systems, how actually data is laid out on the disk, and device drivers will all be done in kernel mode. So the flip side of this design is this is put everything into kernel mode. And the flip side is put the least amount of things in kernel mode as possible. If one of those things has a bug and it kills your whole system, well then less code the better, right? So the other kind of flip side to a monolithic kernel is a microkernel. So a microkernel says, whoa, hold on here. Let's put the least amount of things possible running in kernel mode. So at the very least, you have to manage virtual memory because there's special instructions that you can only access through kernel mode to deal with that. Process scheduling, so you have to be able to steal the CPU away from different processes, so you need a higher privilege level. And then basic IPC to communicate just a few bytes between programs at the very least. It doesn't have to be super involved. And then in user space, you can write your file systems in user space, device drivers, and more advanced types of RPC. So this sounds like a good idea. If anything, in kernel mode would crash it, and then just move everything to user mode. Can anyone think why this architecture might be bad? Yeah. So the privilege levels on the CPU are still the same. Yeah, so, but the kernel is smaller, so in a way it'd be less less hard to hack. Yep.
Slower maybe?
Sorry?
Slower maybe?
Slower. Yeah. Yeah, so it will be slower because we have this boundary between user space and kernel space, and we can only go through that with system calls, right? So anytime you need to support some, new type of hardware or whatever, you have to add more system calls. And also, it's not free to transition from user space to kernel space. It has to go through an interrupt and go do a whole bunch of stuff. So doing system calls is actually slow. If you want to be, fast about things, you just put stuff in kernel space and then hope you have written very good code. So there's other types of kernels. Those are pretty much the two extremes. Most kernels kind of fall kind of hybrid, kind of in the middle, depending on what, whatever developer feels like. So in Windows, in most kernels, some emulation services will be in kernel mode. In Windows, it's in user mode. So it's a bit closer to, it's mostly monolithic, but it has a little bit of microkernel stuff in it. Fun fact, it also has a bit of super macro stuff in it. So back in the day, because that system call interface is slow, Windows decided to put a web server in kernel mode just to make it faster. That proved to be a very bad idea because, hey, if you hack that, you have kernel mode. So that's very, very bad. On Mac OS, device drivers run in user mode, so it's more of a microkernel, right? It has kind of a more clear separation. If you get into research, one of the directions you could go is microkernels are even too big. You can come up with something called a nanokernel or a picokernel that kind of tries to push the boundaries and have even less stuff running in user space. Oh, is that, yep.
I have a question. In slide 21, can we run everything in user space except manage virtual memory?
You have to do process scheduling, at least in here. In kernel space, yeah, because it needs to be more privileged. And it also has to do some basic IPC. I won't go into the research stuff, like even more stuff you can take out of that. But for the purposes of this course, this is like the minimal stuff we can put into it. We won't worry about cutting edge research yet. But yeah, there's, different lines you can draw with kind of different trade-offs. All right, any questions about what we saw so far today? Yep.
What's the difference between kernel and BIOS?
That's a good question. What is the difference between kernel and BIOS? So BIOS is what runs when you first boot on your machine, and it's responsible for essentially booting your kernel. And so it will start, when you start your computer, it's like the most privileged instruction mode, does some initialization stuff, and then it will boot the kernel, and that will be in kernel mode, and then the kernel will initialize the rest of the operating system. And then after the kernel is done initializing, we'll see when we talk about processes what happens after that. But yeah, the BIOS will run first. It's been replaced by something called UEFI, but that's another discussion. But that runs, when you first turn on your computer, that's what executes, and then it's responsible for loading your kernel. And then your kernel boots up the rest of the stuff. Yep.
What's the biggest difference between hypervisor and kernel?
Oh, okay, so that's a good question. So what's the difference between a hypervisor and kernel mode? So remember in virtual machines how you can create a virtual machine that manages, like you can have multiple operating systems running at the same time. So there's special hardware support for that that's more privileged than kernel mode. So it's managing different kernels. So they came up with this hypervisor mode. So we won't see hypervisor mode till like way later in the course, but you can see historically these ring numbers are from x86, and you can see kind of how historically old they are. So ring 0 was designed to be the most privileged level ever. Nothing can be more privileged than that. And this was like in the 70s or something like that. So it got ring 0. And obviously, virtual machines did not exist back in the day, so they thought they were done. And then as soon as virtual machines came out, they're like, oh, they need a higher privilege than kernel mode. Oh, we're at 0, so I guess we have to go into the negatives. So that's why it's called -1. You might also see that there's 2 numbers also missing from here. Anyone hazard a guess as to what they might do? Yeah. Oh, that wasn't a hand that you're just, eh. All right, anyone hazard a guess? Yep.
Like shell and application kind of library stuff, I guess.
Close. Think about kind of between these two, what we threw out. Interrupts, so device drivers, hardware stuff. Yeah, so back in the day, they tried to do different privilege levels. So they tried to separate out device drivers and its own privilege level at like ring 1 or ring 2 in order to have different modes. So you just didn't have user and kernel, so you had more fine-grained control. No one decided to use it. So everyone was lazy. They're just like, yeah, there's 2 modes. So they tried, it didn't work, and that's why there's just a user mode and a kernel mode, and I guess now a hypervisor mode. But they tried to do more fine-grained design and hardware, and no one bought it. All right, any other questions? Okay, well then, let's wrap up. So the important thing to know here is that the kernel is kind of what's operating between the 2 CPU modes. Code running in kernel mode is the kernel. So luckily that's a tautology, that's easy to remember. And system calls are the interface between user mode and kernel mode, and everything has to go through this. So if you write after the lecture, go ahead, write hello world in Python, use strace on it, and just see what happens. And you can use that for any of the programs you've written. I guarantee they will all use the same interface. So we saw the file format and instructions for kind of defining a simple hello world in 168 bytes. We understood, at least marginally, every single byte. The difference between an API, which is just more descriptive, and an ABI, which is like what registers you have to use. And then we saw our first system calls we'll see in this course, and we'll see more next lecture. And then if you have different kernel architectures, it can shift what runs in kernel mode and what runs in not. Typically, you try and get device drivers out of kernel mode. And with that, just remember, I'm pulling for you. We're all in this together. All right.